Greetings, dear audience, dear committee. It's a pleasure to present in front of you my PhD project. Today we are going to investigate the effects of micro and nanoplastics on health. My name is Nicolaus Sándor de Slavnica. I'm a health economist, not a doctor, so I always tell it just in case somebody wonders. I spent my last years analyzing healthcare and different demographics in the financial sector. But back to the topic. The vision of my PhD is, or my vision in general, is a world where environmental factors are not deteriorating human health. The mission which will make this vision come true is to provide the necessary high-quality evidence for policymakers to improve the quality of life. The specific goals here are to investigate the effects of micro and nanoplastics on health in animals, a systematic review and meta-analysis, and the second project is to investigate the same effects of micro and nanoplastics in humans. These projects have been started in September 2024 and November 2024. Regarding the first project, we are investigating the effects of micro and nanoplastics on health in mice specifically. But let me walk you through the background a little bit. 9.2 billion tons. It's a huge number. That is the total amount of plastics which have been estimated to be produced between 1950 and 2017. More than half of this plastic has been produced since 2004. So we see an exponential growth in plastic production, and epidemiologists and toxicologists usually call our times by now in popular articles a Pleistocene, meaning that we have reached a time in history where the damage and the widespread of plastics is, generally speaking, irreversible. It's everywhere. And it will have historical effects on our population and in nature, generally speaking. Regarding how this affects humans in our everyday lives, right? I see plastic bottles, I see clothes, everybody wears clothes. Clothes contain polymers and different plastics. We have three main ways of entry in humans: inhalation, ingestion, and skin contact, since the skin acts as a semi-permeable membrane in some cases, especially at our more intimate parts. The average human consumes around 5 grams of microplastics per week. Just to represent, that's around a bank card, a debit card amount. Therefore, and we have seen in many studies so far that even low doses of microplastics can impair reproductive health, both in females and in males. Yet, we have not been able to conclude how exactly and on what it depends. Therefore, we aim to tackle this threat and systematically investigate the effects of microplastics on health. To further enhance the crucialness of this topic, on the left picture, you can see human sperm, and the green colors are fluorescent microplastics detached to the male sperm, meaning that it already contains sperm as of now. On the right side, you can see a placenta, a female placenta of a human, and the red dot represents microplastics seen in the placenta, both individually present in the male and female reproductive system. So what will be the clinical question here? Well, our clinical question is, what is the effect of micro and nanoplastics on the male reproductive health in mice, and how does the effect depend on the properties and dose of micro and nanoplastics? We chose a PICO framework. Population is mice, exposure is micro and nanoplastics, comparator is no microplastics or nanoplastics. And the outcomes we are measuring are sperm viability, sperm morphology, tubal diameter, epithelium thickness, Johnson score, tunnel positive cells, BAX and BCL2 ratio, and inflammatory markers. We hypothesize that micro and nanoplastics worsen male reproductive health outcomes depending on dose and type, such as size, way of entry, and chemical composition. Why male mice, one might wonder. The male mice are most represented in reproductive studies, and they are more representative than than female mice when it comes to reproduction, since the female mice have a cycle of 5 stages, whereas humans only have 5 stages. So mice are more representative, even though a limitation of the study is that it is an animal study. The clinical and research implication are intended to be recommendations on environmental MMP levels, where to focus funds and what should be measured, and further, what is the social burden of micro and nanoplastics. We found 1,816 articles, of which we, after duplicate removal, resulted in 1,167 articles, which we further reduced down to 134, resulting in 78 full-text articles. In this moment, I would like to thank my co-investigators, Sila Salsa and Rena Hirose, for the great amount of work they put into this project. Our topic is feasible. We have successfully registered our Prospero. Duplicates have been removed. Title and abstract selection is done. Full-text selection is done. Data extraction is done. Risk of bias is in the making, and figures and tables are partially already shown. We are yet waiting for the statistical analysis to be finished from the statistical team. And here I would like to show you my first figure. This forest plot shows the measured sperm count in exposed mice compared to the control group of micro and nanoplastics. The boxes show the main difference and their standard deviation. Most studies are slightly tilted towards the left side, which means that the sperm counts are lower in exposed mice. On average, exposure to micro and nanoplastics reduced sperm count by around 6 million per milliliter, and the variability between studies is extremely high. On the second figure, you can see here we repeated the analysis after excluding studies which are less precise on estimated data. The effect is still clear and consistent. Sperm counts as exposed mice after exposed to micro nanoplastics have a slightly less reduction in sperm count, therefore still yet very strong, around 3 million per milliliter. But if I go back to the first study, on the top you can see a study from Tombul, which seems to be an outlier, but this is generally speaking because of the high baseline of sperm counts, which was around 180 million per milliliter, whereas most other studies show the baseline of 4 to 8 million milliliter per mice. Further, Tombul used the measurement to establish micro nanoplastics in a Mackler chamber, whereas other studies used the hemocytometer. This further on, when it comes to the statistical part, micro nanoplastics were shown as standard error of mean, whereas in most studies it has been shown with standard deviation, which also further make it look like it is an outlier, whereas this is more a question of measurement rather than biological differences, and the findings of Tombul are coherent with the general trend of micro nanoplastics reducing the sperm count of mice. Our I-squared is around 93%. This is extremely high, which shows that we have variability based on dose, polymer type, way of entry, and size. Strengths and limitations of this project. The strengths is that we highlight the potential risk factors influencing male reproductive health outcomes. We show detailed extraction of microplastic characteristics such as polymer, size, dose, route, and duration of exposure. Offers clear directions to further research. And the limitations of the study is that this is a retrospective design. Dependence on digitization of graphical data may introduce minor measurement error, and findings are based on mouse models. Implications for humans or health are therefore limited. Regarding the second project, we are going to investigate the prevalence of micro and nanoplastics in different human tissue samples. To the background briefly, because I'm a little bit out of time, many studies shown that we have incredible amounts of microplastics in different human tissue samples. Looks like it specifically triggers the brain. We also know that micro nanoplastics, the amount of micro nanoplastics is way higher in people with dementia. We also know that it is found in testicles and general reproductive system. It very much likes the organ systems. Muscles are an exception for this, for example. So the vital organs are favored by micro-nanoplastics so far, preliminary. The clinical question, therefore, will be, what is the prevalence and distribution of microplastics in human tissue samples, and how does this vary across different demographic factors? We chose the COCO-POP framework, where we use micro-nanoplastics, investigate tissue samples, and the population will be humans. We hypothesize that micro-nanoplastics prevalence differ among different human tissues. What is the prevalence and distribution of microplastics? Oh, sorry, wrong direction. Yeah. The project has been declared so far feasible, yet we focused on the first project, which we had to narrow down on one population. We planned on having it with many more populations, but that was too much of a big fish project. And I would like to close my presentation with a very interesting quote of Albert Einstein, and referring back to the Pleistocene I talked about. When we had some sorts of epidemics, such as lead in previous generations, we just, or when the ozone layer was decomposing, we just banned some substances, and somewhat the problem got solved. In case of micro-nanoplastics, this is impossible. We cannot do this. It's too widespread. It's too micro and nano. So we cannot solve problems with the kind of thinking we employed when we came up with them. And here I would like to thank you for your kind attention.
Thank you very much for this interesting presentation. Are there any questions? Please.
Thank you for your presentation. My question would be that how can mice meet with this nanoplastic? So how were these experiments in the articles?
These were experimental studies without exception. So pathogen-free mice were acquired from different suppliers, and they were exposed to microplastics in an ultra-sterile environment. And then they always had a control group which was non-exposed, either with ultra-pure water or saline or maybe corn oil. And then there were different exposure groups dependent on size of micro or nanoplastics and dose and duration, for example.
Thank you. And then with what type of measurement were these, so the level of the nanoplastic measured, or from what type of tissues were the measurements done?
Like, as in which tissue was investigated of mice?
Yes.
Usually it was the testes, the epididymis, or different parts of the epididymis, like cauda, for example. But I only focused on reproductive health and sperm outcome as my primary outcome, sperm count on my primary outcome. So therefore, we didn't investigate other variables such as lung tissue or kidney or liver, which were also many times represented in studies.
Thank you.
Regarding, because this is a meta-analysis with
yes.
several different experiments included, did these conditions that you mentioned apply for all studies, that everything was done in a sterile condition, every experiment, every study included followed the same experimental routes?
Can you clarify what you mean on the experimental route?
You mean that this is a meta-analysis?
Yes.
That, as I saw, that there are several studies included.
Absolutely.
And you told in the previous question that it was done in an ultra-pure environment.
Yes.
But is this valid for all experimental
without
studies?
Exception.
Without exception.
Only laboratory studies with similar or same environment statistically poolable.
There has to be some difference, because I think that the mice used is probably not the same breed in every experiment, so that could be a source of difference. But as you don't have the statistical analysis yet, I don't know whether you have an answer to this.
Well, we are not done with the full statistical analysis, but so far what I can tell you regarding the species or specimen of mice, usually it was bulb mice in the overwhelming cases. Sometimes it was Kunming mice or ICR mice, but the overwhelming majority was bulb mice.